No. Good afternoon, everyone, and welcome to those of you watching online. Just a quick housekeeping. If you are planning to tweet, please make sure your devices are on silent, or if you're not tweeting, then ideally switch them off. Thank you very much for coming along to the first of this term's seminar series. If you've been on our website, you'll see we have a very diverse range of talks on the theme of climate change and what can we expect in the lead up to COP in Paris in December. We're going to start this week with taking a step back and really looking at the human impact on the planet. But before we do that, I just want to give a plug for what's coming up at the Oxford Martin School if you haven't seen the full range of events. On the 7th of February, over in the at the Maths Institute, we have a wonderful one-day conference organised by an undergraduate group called 21cc. There are still places available for that, and you don't have to be an undergraduate to go. It's a fantastic day of debates around some really good, interesting, gritty issues. Then on the 2nd of March, we have our second annual International Women's Day lecture. We're very privileged this year to have Dame Sally Davis, who is Chief Medical Officer for the UK. She's going to be talking about the ticking time bomb of antibiotic resistance. That is very likely to be a complete sellout, so do register early for that one. And on the 11th of February, we're again very privileged to have the chess grandmaster Garry Kasparov coming once again to the Oxford Martin School. And this time he's turning his attention to artificial intelligence and the limits of human performance. So those are three key events coming up. But back to today, I'd like to welcome Yadvinder Malhi, who is Professor at one of our institutes, the Centre for Tropical Rainforests. He has a great long list of credits to his name. He's Professor of Ecosystem Science at the School of Geography and Environment and the Environmental Change Institute, and also the Jackson Senior Research Fellow at Oriel College. He's an ecosystem scientist who explores the functioning of all the biosphere and its interactions with the atmosphere. And he has a particular fascination and love of tropical rainforests. So today, like I say, he's going to be taking a step back and looking at a bigger picture of the human impact on the planet. Welcome.
Thank you very much. Can everybody hear me fine? Okay, great. Okay, do the lights go down a bit, or is this the normal level? Okay. I'd like to start with one of these images that has become quite popular these days. I have it as a screensaver on my desktop. So let's go. Okay. Is that? Let the lights calm down for a second. Okay. The image is going funny as well. But anyway, this image. Let's start that again. Let's have this comment. Let's start that again. Very good. Okay, let's start with this image. Okay, this is the image that's become quite popular now, quite famous. It shows the lights of cities largely at night, superimposed on the Earth. And I find this image both mesmerizing and troubling. And it's mesmerizing because we can see the sum of our global activities, and over time we can see changes. Some of them are which are fascinating and aspirational. We see electricity spreading across rural Asia, across rural Africa, and bringing a variety of benefits to vast numbers of humanity and people being lifted out of poverty. But it's also, at another level, a troubling image because we see all that mesmerizing activity is sitting on a thin skin, a few centimeters of soil, a few meters of biosphere, and it sits under a few kilometers of atmosphere. And we're not managing any of those reserves in any sensible, planned way. We're conducting a huge experiment in the functioning on this planet, sitting on this thin skin. So the broad question that I'm looking at is, how did we get here? What are how can we measure how large we are compared to the natural processes that maintain this skin and the functioning of this skin? And how has this changed over time? And how is it likely to change over this century? So the whole series is about climate change. In this talk, I'm actually going to step back one level beyond that and recognize that climate change is actually just one dimension of a more general challenge we have, which is the challenge of the Anthropocene. And this is the challenge that we, as a species, in our total activity and the total number of people we are, but particularly in the activities we conduct, are large compared to the natural geochemical processes of the planet. And if we solve the climate change problem next year by some clean technology that didn't emit carbon dioxide and other greenhouse gases, I think we'd still be facing the fundamental challenges of managing our planet when we're large compared to the natural processes of the planet. And climate change as being the waste product of activity is just simply one aspect of this challenge that we face. So the question I'm going to look at first here is, how do we measure how large humanity is relative to the Earth, and how has this size varied over all of human history? And this, although it's in this climate symposium, is actually a chapter in this book that's based on a series that the Martin School ran last year on what called Is the Planet Full? So if you want to look in more detail at some of the arguments and some of the references, they can be found in my chapter in this book. When we look at then there's a number of ways of measuring the natural biogeochemical processes of the planet, but one simple metric of biological activity of the planet is what's called net primary productivity, the amount of organic matter in produced per unit area per year. And if we do, using satellites and field observations, and we ourselves are involved in much of this work in the tropics, you can produce maps like this that show how global productivity, the global metabolism, you could almost say, of the biosphere varies across the land. And you see that the largest contributors are the tropics, where you have year-long productivity and warm temperatures and no winter or no dry season in the wet tropics. But there are other significant patterns, and there are also areas of low productivity, such as the large deserts, such as the Sahara. If we look at the oceans, we see a very different pattern, and here the constraint is nutrient supply rather than climate, and we see that the upwelling zones on the edge of continents are the zones of really high ocean productivity, and the huge ocean deserts, much of the ocean, because of nutrient starvation, is a desert in terms of productivity. So we can understand, in terms of this unit of productivity, what the natural metabolism, we could say, the biological metabolism of the biosphere is. And the question I want to look at is, how does this compare to the metabolism of humanity? And to do this, we need to go beyond just the idea of biological metabolism. Every living organism has a biological metabolism. We all use chemical energy in various forms to power our activities, to maintain our bodies, to just maintain our cell functioning, and whether they're plants or animals or any type of living organism. But humans fall into a class of a few organisms, they're not the only ones, that have a significant social or extended metabolism. This was a concept that was introduced by industrial ecologists in the 1990s. And what we mean by a social metabolism is that we all, as well as using energy to maintain our own body functions, we use energy in lots of other ways in our social activities, whether it's in transport systems, in urban infrastructure, and we have a much more significant use of energy, flow of energy to do work. So in that sense, it is a metabolism, but it's not linked to the biological maintenance and activities of our physical bodies. So this is termed, I term this the extended metabolism or social metabolism in this talk. And so just to introduce this idea, let's look at how biological metabolism and social metabolism has varied at different stages of human prehistory and history. And the basic unit of metabolism is the watt, the joule of energy used per second. And just to calibrate you, if you're not familiar with these units, an old-fashioned typical tungsten light bulb is around 60 watts of energy, so 60 joules of energy being used per second in this. And my idea in using metabolism not only a metric of our impacts, but it's generally a metric of how much we're able to alter the world around us. If our metabolism is small compared to the metabolism of the processes, we have a relatively small potential to alter through our activities the processes around us. Whereas if our metabolism dominates over other processes, then we have the ability to radically transform the systems around us. And so let's go back to the late Pleistocene or early Holocene to a world where everybody is a hunter-gatherer. So there's no agriculture yet, and so humans have expanded out of Africa, have covered much of the planet's surface, but live in a hunter-gatherer mode of life. And so the first thing is to recognize our basic biological metabolism. That hasn't changed much over that time. An active human typically burns around 120 watts. So we have the equivalent power, chemical power burning through us, equivalent to 2 tungsten light bulbs burning all the time in our bodies. And that's our basic biological metabolism. But even hunter-gatherers have an extended metabolism. They use energy for fire. There's inefficiencies in the way they gather energy from the surrounding environment. And so their extended metabolism is much larger than the basic biological metabolism. It's around 3 times the size, around 300 watts. And the absolute value varies a lot from society to society, where this has been calculated, but it's a few times larger than the basic biological metabolism. But one feature of a hunter-gatherer life is that you have to just make do with what you can harvest from a largely natural ecosystem, whether it's harvesting fruits or berries or hunting for wildlife. And this mode of drawing food or energy from the environment can only support very low population densities. They're typically on the order of 1 person every 10 square kilometers. There's a typical population density that's maintainable by a hunter-gatherer society. And so if we multiply that metabolic rate, or 300, by that population density, we can calculate that the metabolism per unit area is around 30 watts per square kilometer. So a low-power light bulb, or half an old tungsten light bulb, per square kilometer. So the total energy flowing through this hunter-gatherer society is a tiny fraction of the energy flowing through the biosphere as a whole. So if we take, for example, a tropical savanna environment of the type in which we all evolved in Eastern Africa, we can calculate quite easily the total energy, the chemical energy flowing through a tropical savanna environment, and it comes out to be around 30 megawatts per square kilometer. This is the chemical energy, not the pure solar radiation, but what's being captured through photosynthesis and then being processed and being consumed at different parts of the ecosystem. And comparing that to the hunter-gatherer social metabolism, it was only around 0.0001% of the biological metabolism of the savanna. And this didn't mean that hunter-gatherers didn't alter the environment. The use of fire would have changed the nature of the environment. Their hunting out of certain animals may have changed the ecology and functioning. So they still had an influence on the environment, but it's relatively small overall in their capacity to change these powerful biological forces that are determining the nature of that environment. So this all began to change in the early Holocene with the advent of the agricultural, the Neolithic revolution, where people stopped being hunter-gatherers in certain societies and began to actively modify the ecosystems around them to optimize the production of useful materials, in particularly food and fuel wood. And the origins of agriculture are fairly so they're a subject of quite intense research, but they're fairly well described in the sense that we know that it originated independently in many regions of the world, not just in the Middle East and China, which is well known, but in some surprising regions like New Guinea and in the Amazon and the Andes and the Andes, amongst others. And one of the fascinating things that it had so many origins at around the same time, after hundreds of thousands of years of human history, which seemed to say that there was something ripe in the way our societies were beginning to organize our communication systems, our use of language, that once the climate stabilized enough at the end of the last ice age, it was almost inevitable that agricultural societies would pop up in different parts of the world. The fact that they appeared independently in so many different places. the key feature in terms of this talk about agriculture, it is the active colonization of ecosystems. So rather than just reaping off what we can gather from the ecosystem, we start modifying the nature of the ecosystem in quite a fundamental way, choosing what crops are in there, removing competitor crops or possible herbivores that could damage our crop yields. And this has led to a gradual increase of this agricultural metabolism. We're appropriating much more energy from the surrounding ecosystem. And if we now take some values estimated, say, just around the 17th century for Europe, and these are values that were calculated for Austria around the 17th century by Habel and others, the extended metabolism of this agricultural society is now much larger than the basic biological metabolism. It's around 2,000 watts, so about 20 times larger than the basic biological metabolism. And that's in all the various domesticated animals we use to power or to provide indirect foodstuffs such as meat and dairy, and also in the way that we've sort of modified surrounding ecosystems to appropriate the food for our production or for our consumption or for the consumption by our animals. But one key advantage, which is why agricultural societies in most areas have outcompeted hunter-gatherer societies, is that you can support much higher population densities on an agricultural society. Typically, by the 17th century, it was around 40 persons per square kilometre. So if you multiply those two numbers together, you get a social metabolism of a pre-industrial agricultural society of around 80 kilowatts per square kilometre. And if we compare that to the metabolism of a temperate forest, a woodland that would have been replaced by a Northern European agricultural society, this metabolism is around 5% of the natural ecosystem metabolism. So yeah, it's beginning to become substantial, and it's reflected in the very altered landscapes, but there's still a fair bit of natural biological process in these pre-industrial agricultural landscapes. And we can, using this, we can track how metabolism has varied through history. And here I draw on some data from the popular historian Ian Morris, who wrote a book called Why the West Rules for Now, and in the appendix he has data on energy use by Eastern and Western Eurasia since pre-agricultural times. So drawing on that, there's meticulously researched in terms of looking for various strands of evidence for this. And drawing from that, I converted them into units of social metabolism. And so you end up with this graph. Firstly, to define what is meant by East and West. So East is the great China and the surrounding regions, the greater China region, but particularly China. West here is a definition that encompasses everything from the Middle East to Western Europe and all the way to Western Europe. And the idea is that many aspects of Western society originated in the Fertile Crescent in the Middle East, fed through into Egypt and then to Greece and Rome and then and into Europe. So that's a broader definition of the West. And in this analysis, I won't go into the details of it in this talk, there's an argument that this early origination of agriculture in the Middle East, as we would call it now, gave an advantage to Western Eurasia in terms of metabolism. Asia was a few millennia behind East Asia, and there's been this gradual rise over time. But one interesting feature is that it hasn't been a simple linear rise. There are periods of hiatus where there were obvious problems going on, and then there were periods of rapid rise once those societal or structural problems seemed to be solved. And particularly, and I have cut out the last few hundred years here, so this stops at about 1700 for now. You'll see what happens more recently later. And if you zoom in on the last few thousand years, we see something a little bit startling, perhaps, that we would have thought, naively, that perhaps human activity has risen quasi-uniformly throughout history. And what we see is evidence of a peak in the West around the time of the Roman Empire. And then fairly much bouncing along in these data on metabolism since then, until about the 1700s. And in Asia, you see the Han dynasty seemed to have a slower social metabolism than the Roman Empire, but as in the post-Roman, in the Dark Ages of Europe, China leapt ahead around the time of the Song dynasty. So there seemed to be, but in both cases, there seemed to be a flattening out of this rate of rise. And there are many there's a whole range of history here, so I have to try to tread with caution in interpretation of this. But there were many proximate factors for this. Famine, barbarian invasions from the Central Asian steppes, lots of other factors. But I would argue on one level, this was also a society that was constrained in terms of energy supply. So when shocks to the system came, be it disease, pandemics, or nomadic invasions, the system didn't have the capacity and energy to respond to those shocks. And therefore, it was bouncing along at this cap. And possibly, I would argue, one of the fundamental reasons why things flattened out is that these agricultural societies had become full in terms of their modes of energy production. Using that agricultural mode of energy production, they couldn't get significantly more energy out of the systems, the energy systems that they had, where they draw energy purely from agricultural areas. And one constraint with an agricultural mode of energy supply is the amount of energy you get is largely dependent on how much land you have. You can have inefficiencies over time gradually, but really if you have twice as much land, you have twice as much energy available. And inevitably, you start having constraints on the supply of land as populations increase. So these systems were bouncing around, and in some senses it could be argued that they were full. This was a Malthusian world where increases in productivity just led to increases of population and no overall strong increases in welfare over this period. And then something fascinating was happening in Song Dynasty China around the 13th century, where coal began to be burnt, and it was almost at the brink of a fossil fuel revolution, but didn't quite happen for a variety of factors. And then in the 17th century, something did happen in Western Europe, which is that this energy trap was broken by a technological advance. And that advance was the utilization of fossil fuels. So rather than using the energy of the biosphere that's immediately available to us in terms of productivity of agricultural systems, we could tap into the ancient energy of the biosphere, the energy trapped by forests millions of years ago and buried in deep deposits in the earth in a highly enriched form. We discovered the ability to tap those sources of energy, and that intensity of energy led to a period of rapid increase in our social metabolism, with a lot of negative consequences in terms of carbon dioxide emissions, but also in terms of pollution, urban air pollution, and many other negative consequences from that, but also a consequence in terms of the amount of energy that was available to break us out of this agricultural energy trap. And so we move on now to the early 21st century, a world that is increasingly urbanized. Over half the population on the planet is now urban in some form or another, or another significant other part is peri-urban. And so let's look at the metabolism of a modern industrial urban society. Before I get onto society, one thing I want to emphasize is that much of this talk and this series is about the hazards and the potential negative consequences of our large metabolism in its broad form. There are many good things that have come from the fact that we have a large social metabolism. And you could look at a range of statistics, but just as examples, the decline in mortality, the extension of lifespan, the extension of health systems, things that we can often take for granted when we look at the environmental problems of our time. But compared to where say, Britain was a century ago, the expectation that our children will live to adulthood, these sort of assumptions that we take for granted are actually assumptions of the current phase of the Anthropocene, where we have enough energy to develop sufficient infrastructure and health systems and education systems that allow for these. And the ongoing pressures of the Anthropocene are as many of these benefits are extending out to large areas of humanity that haven't had access to those benefits and those assumptions until now. So the forces that have brought about the Anthropocene have certainly brought about much that is good to humanity, and we mustn't forget that. But let's move to a modern industrial society. And here I've got values for England, and these are only for England rather than for the UK as a whole, for the last decade. And we estimate a social metabolism of the average person in England in terms of our total energy use is around 8,000 watts. So it's gone up 4 times from the pre-industrial agricultural society. And a key feature now is that our energy system isn't dependent on land anymore, but it uses this largely a fossil fuel-based system for other intensive forms of energy as well. We can support much higher population densities on that energy system. And in England, it's around 400 persons per square kilometre. And if we compare that, we can calculate the natural metabolism of the English biosphere, or the ecosystems in England, particularly if in a pre-altered state, and that would be around 200 gigawatts, the amount of biological energy flowing through the woodlands and grasslands of England. And so, but if we work out our human metabolism, multiplying the per person metabolism by the number of people per square kilometre, we come up with an extended social metabolism of 400 gigawatts. So the total amount of chemical, biological energy flowing through the population of this country is twice as much as that which flows through the biosphere of this country. And how is that possible? Well, there's a number of reasons. One, not all of that energy comes from the biosphere itself. By using fossil fuels, we're tapping a source of energy that doesn't directly impinge on the productivity of the biosphere. But the other reason also is that we outsource much of our energy in terms of using products that are made in China, other food products that come from around the world. We're outsourcing much of our metabolism to other regions of the world where there's still surplus metabolism, and being a net import of the metabolism from elsewhere. And so, in the case of the US, in the UK, we are approaching around 200% of ecosystem metabolism. If you calculate this for somewhere like North America, the number's smaller. It would be around 50% of ecosystem metabolism because of the large empty areas in the middle. But if you focus on areas like California or the East Coast, you would get similar numbers to Western Europe. And one way of looking at this is through this, by looking at carbon dioxide emissions, because most of our metabolism is still in the form of coal-based or carbon-based metabolism. These plots of carbon dioxide metabolism can give us some insight. So it's rather than seeing these as CO2 emissions, as I'll show you in a moment, think of this instead as a map of metabolic activity over the last 300 years, the biological activity of the human activity of different parts of the biosphere. So as you see, going in 1750, it's all beginning to happen in this small island off the west coast of Eurasia, with the Industrial Revolution kicking off, and you see this patch of blue there beginning to spread by 1820 into the Low Countries, into France and Germany, but still much of the industrial metabolism elsewhere is low. Then by 1870, you start seeing the eastern part of North America lighting up with this industrial metabolism, but Germany and UK are blazing yellow hot at this stage. And then by the mid-20th century, you see Japan is lit up, but also significant other parts. And since from the 1960s, you see a big transition, what's often called the Great Acceleration. And you see this industrial metabolism spreading around the world. And this has led to the world that we see in these images of lights blazing across the planet in the 21st century. So one question to ask is how much of this metabolism is directly drawing from the contemporary biosphere? What's the direct impact of this metabolism on the biosphere? And here's in the background, I have an image of road expansion in the Brazilian Amazon. And one of the features of, you could argue that if there was so much metabolism being drawn from other sources, maybe we would reduce our impact on the biosphere. And in some cases that is true. If in the case of Europe, the fact that we don't draw our fuel supply from woodlands anymore has meant that many of Europe's woodlands and marginal agricultural areas are actually seeing a recovery of woodlands from the intense pressure of the last 1,000, 2,000 years. But on a global scale, this entire enhanced metabolism enables us to do things like cast roads across the Amazon, railroads across the Americas. So actually enables us to, and also to capture nitrogen from the air in industrial processes. So it enables us to enhance our impact on the biosphere rather than reduce our impact. And so Hubble is trying to calculate this term. So of our metabolism at the moment, globally, about half of it comes from the direct use of biomass, either for food or for fuel. The food can be directly for our animals as well. And the other half comes from other energy sources, which is still overwhelmingly fossil energy, although nuclear and hydro and geothermal and renewables play some part in the last few decades in that component. And if we look at that impact on the biosphere, another metric that's sometimes used is the human appropriation of net primary production. How much of the productivity of the biosphere is being appropriated for human use. And what we see here are interesting patterns. The highest levels tend to be in the heavily industrialized and intensively industrial agricultural countries, regions such as Europe and hinterland and the agricultural hinterlands of North America. But also other significant areas include some of the old ancient agricultural societies, such as India and East Asia, where you see very heavy, high population densities, very heavily dependent on the surrounding landscapes for their agricultural foodstuffs. And some of the lower ones tend to be in parts of the tropics, in the Americas, and one reason to speculate here why this is so low in the Americas is the huge population collapse that occurred in the Americas after the European discovery of the Americas and the ensuing disease that wiped out up to 95% of the population of the Americas at that time. And that may be one of the reasons why we don't see these dense patterns that we see in Asia where that population collapse didn't occur. So just to take a slight detour for a few minutes, let's go back to this idea of metabolism. And one of the early advocates of this idea of metabolism was a scientist, Max Kleiber. There's a photo of him there. And he advocated he measured the metabolism of lots of organisms and advocated what is perhaps one of the few laws in biological sciences. And this was how the metabolic rate of an organism varies with the mass of that organism. And what you find is if you plot them on logarithmic scales, within any type of organism, you tend to get quite a straight line. So there's an offset, but cold-blooded organisms form a straight line relationship in these logarithmic scales. Warm-blooded organisms generally have a higher metabolism than the equivalent size of cold-blooded organism, but also within warm-blooded organisms, you get a straight line. And this has been termed Kleiber's law. And this is, because it's a log-log scale, essentially what this describes is what's called a power law. And just to briefly explain what a power law is, what this advocates is that the metabolism is some function, some constant, arbitrary constant, multiplied by the mass of an organism to the power of a variable called alpha. And if we convert these into logarithms, if you have a log of biomass, it's equal to the log of this constant, which is a constant, plus alpha times the log of mass. So hence what this means is that if we plotted the logarithm of metabolism versus the log of mass, we get a straight line, and the slope of that line, alpha, if that line is straight, that slope is this scaling coefficient of this power law. And what Kleiber's law was suggesting is that for biological organisms, that alpha tends to be around 3/4. So it's not 1. It tends to be less than 1. And one of the consequences, there's a variety of consequences of that. Kleiber's law suggests that metabolism scales as body mass to the 3/4. If you divide this by mass, you get the metabolism per unit mass scales as mass to the -1/4. So what this means is a unit mass of a large animal, a unit mass of elephant, has a slower metabolic rate than a unit mass of mouse. So as things get bigger, an elephant has a bigger overall metabolism than a mouse, but per unit mass of elephant is actually operating at a slower speed than a unit mass of mouse. And many biological processes of rate, reproduction rate, heartbeat, tend to scale according to this law. So the heart rate of an elephant is slower than the heart rate of a mouse. And many times in biological organisms are the inverse of this rate. So lifetime, gestation time, how long food stays in your gut tends to scale as body mass to the quarter. So food stays in an elephant's gut longer than it stays in a mouse's gut. And one of the consequences is that if you multiply the rate by a time, you get a constant. And so the number of heartbeats in a lifetime across organisms is approximately constant. A mouse has about as many heartbeats in its short life as an elephant has in its long life, because the scaling constants. And this has been shown again that many biological organisms broadly follow this rule. There's some arguments around exactly the nature of the rule. And so we can calculate the biological metabolism of different masses of animal and plot them on this log scale as a straight line. So a dog's here, a human's there, a bull's there, a rhino, an elephant. And one question we can ask is, but this is only showing biological metabolism. Let's bring social metabolism into this picture. And we all have a huge social metabolism, much bigger than our biological metabolism. How big, the question I'm asking now is, how big an animal would we have to be for our biological metabolism to be the same size as our social metabolism? So you get an idea of how metabolically big you are. And we can do that. And I've given you numbers already to do this. So for a hunter-gatherer, the social metabolism is slightly bigger than the biological metabolism, but not more. So the hunter-gatherer is like a large human in terms of their social metabolism. For a pre-industrial agriculturalist, the metabolism is approaching a few thousand watts. So it's the equivalent metabolism of a rhino, the biological metabolism of a rhino. And a modern industrial human has a biological metabolism of around a 10-ton primate, so bigger than the metabolism of an elephant. And the North American has an even larger one, more like a 15-ton primate. Well, actually, there's 15 tons for a European and 30 tons for a North American. So if you want a vision of what impact we're having, or say on the UK alone, imagine England being a country of 50 million 15-ton King Kongs roaming the landscape. And you can see inevitably we have a large consequence on the as we're consuming resources, demanding resources, we're having a large consequence on the environment around us. And there's some other really interesting quirks that can emerge from this metabolic viewpoint. One interesting one is here. One of the fascinating aspects of contemporary times is what's called the demographic transition, which is as societies get wealthier, they tend to have less children per person. And that's one bit of good news in terms of our environmental demand on the planet, that in many cases the rate of decline of fertility has been much larger than even was expected 20, 30 years ago. So countries that we associate with very large populations have become, in many parts of the world, relatively small numbers of children per couple. And there are lots of ways of explaining it, but you can also look at this from a metabolic viewpoint. If you look at the metabolism, biological metabolism of various animals, the larger the animal, the less children it tends to have. And if we look at primates, we see small primates tend to be up there with other animals. Large primates, these black dots, tend to have a lower metabolism, so deviate from this curve. And that's partially because a lot of primate metabolism is used to maintain brains and very expensive organs that other animals don't have. But then if you look within the primates and then look at pre-industrial agriculturalists, which are around here, you see they fall on this curve. And then look at modern nation states, these open circles, they fall on this curve. So one interpretation of this is that the relationship is consistent. And is that when we raise children now, we're not raising biological, for ultimately 50-kilogram primates, we're raising 15-ton primates metabolically, and they're costly to raise. They demand a lot of resources. We invest in only having one or two typically of these 15-ton primates rather than the 6 or 7 we would have had when there was less metabolic costs. So that's one way of viewing this. The notable exception to this are these triangles here, which are Middle Eastern societies, which have an abundance of energy resource and seem to still have, at least in terms of the citizens and not the transit worker population, seem to have very high fecundity and high consumption rates. These are states such as the Gulf states. And so now look at metabolism at this global level from this perspective. And we can calculate the metabolism of the biosphere, land biosphere as a whole in this case, and it's around 150 terawatts of metabolism. And if we estimate the global social metabolism of humanity on these different time scales, the pre-agricultural metabolism was around 0.002% of this land biosphere metabolism globally. The pre-industrial metabolism agricultural metabolism was substantial. There were areas of the world, such as Europe and India, where we had a large agricultural metabolism, but considered globally, considering the vast areas of tropical forests and Siberian wildlands, it was still only around 2% of global land biosphere metabolism. And if you go to the modern human extended metabolism, there's obviously significant error bars around these estimates, but it's around 17% of the metabolism of the land biosphere. Now, depending on your perspective, that's large or smaller than you expected, but it is a significant number compared to the natural processes of the planet. And it suggests it's one way of measuring how large we have become compared to the natural biological processes. And I would argue that many of the challenges we face are to do with the fact that our metabolism is large. When we think of climate change, it's fundamentally a problem of waste production. Our metabolic waste in the form of CO2 is polluting the finite space of the atmosphere and altering the basic radiation balance of the atmosphere. When we think of biodiversity loss and habitat loss, it's because our metabolism is converting and altering the ecosystems of the planet. So many of our problems can be framed, if you think of resource supply, it can be framed in terms of the demands of this increasing global metabolism. And so let's look forward to 2050. And if we take a UNDP mid-range projection, we're looking at a global metabolism of around 32% of biosphere metabolism. We could consider something like a global China, where everybody in the world has the energy use of an average Chinese citizen today. And many of us are here in this room have a much higher energy use than an average Chinese person. And we're looking at around 40% of biosphere metabolism. And if we take a global US, where everybody has the life standards of of an American, we are approaching 120% of biosphere metabolism. And we have to be cautious how to interpret this. What number is an ideal number? The larger this number goes, the less of that metabolism is available for the maintenance of everything else we value about the Earth. The richness of biodiversity, energy used by other species, the life support systems of the planet itself. So this is not an idea that we have a certain amount that we have to get up to, but it just gives a measure of how our influence is compared to these biological processes. And it also summarizes the huge challenges we have with this rapid increase of this metabolism, the rapid expansion outside of Europe and North America of this industrial metabolism that is occurring at this moment. And the fact that it starts hitting these limits associated with this global metabolic production. So if we now, and I had left this off in previous slides, if we now include the post-industrial period, what we see is after this gradual expansion of social metabolism, this cap that seemed to be hit around the time of the Roman Empire, bouncing around, this release associated with the Industrial Revolution, and then this period of essentially metabolic free inflation, free expansion into energy space, with this huge amount of energy released by the Industrial Revolution. But what we foresee is that this boundary has been passed, but it's inevitable that we're hitting at other boundaries. And the boundaries that I think that we're hitting are planetary boundaries associated with the limited size of the planet and the planet's metabolism compared to our biological metabolism. And climate change is just simply the most prominent of the aspects of these boundaries that we're hitting. And this approach of planetary boundaries has been popularized by Rockstrom and Stefan and others, and this is a paper that just came out last week that uses this idea of planetary boundaries, that there are various limits to how much we can alter basic support systems of the planet. And in some cases, we may have already passed some of these aspects in terms of biosphere integrity and biogeochemical flows. And fundamentally, these are built around two boundaries, which are the atmosphere and the integrity of the biosphere in this framework. And so to summarize this part, many pre-industrial societies, I would argue, there's evidence that they may have been full according to the technological modes of their time. They were bouncing around energy use at a fairly flat level. The Industrial Revolution opened up access to previously unavailable energy from deep time ecosystems, and we are still in a period of this huge metabolic inflation that we've come to regard as normal. It's become our default assumption that we keep on growing our energy use, our economies, our societies year on year. But this assumption is only a few generations deep and is not the norm for how most of humans have lived throughout human history. And this period is now hitting constraints in both resource supply and waste production, constrained by the size of the planet's systems. And this, I think, is the fundamental challenge of our time. So just for the last few minutes, I'm going to have a little focus on one aspect of modern humanity, which is the fact that we're a predominantly urban society, or an increasingly urban society. Over half of humanity is urban, and more is becoming so. And if we look at it, we see that it's outside of Asia and Africa for now, most of humanity is overwhelmingly urban, when you include small towns in this definition as well. And so let's look at the functioning of cities in this metabolic framework for a second. And one question I want to ask is, it's often used as a metaphor. Can we apply it as beyond a pure metaphor? Are cities, in some senses, superorganisms, biological, social organisms? And the analogy I want to take is from the social insects, who invent certain types of social insects, particularly ants and termites, invented agriculture long before the Neolithic Revolution. This is a nest of a leafcutter ants in South America, which has been excavated by scientists. It's a huge structure, and these ants basically get their foodstuff by harvesting organic material and growing a fungus, taking it back to their nest, growing a fungus on it, and eating that fungus. So they're essentially farmers. And this is a farming system that was developed many millions of years ago. And one of the questions that we can ask is, so these are, in some ways, the closest approximations to our social societies. To what extent, how does the metabolism of an ant society compare to the metabolism of an individual ant? How does it scale? And then we'll look at cities in a moment. And some work has been done on this, looking at ant and termite societies, which termites are the other great social organisms. What we find is that the same metabolic law seems to apply. The slope is slightly different. It's around 0.8 rather than 0.75, but it's pretty close. And if you look at colonies, ant or termite colonies, they seem to broadly follow the same rule as individual ants or termites. And this is approximately 3/4 scaling rule. And what that means is per unit mass of termite, a large colony, the termites do less than in a small colony. And it's a bit of a mystery trying to understand exactly why. Why do termites do less when they're in a large colony? Is it efficiencies in how they stratify work? Is it that they move around a little less because tasks are divided between other termites and foragers and things? But somehow the metabolism per unit mass of a large ant colony or a large termite colony is slower than the metabolism of an individual or of a small colony, for example. And now let's go to. I think let's get this. So now let's go to human societies. But let's ask this question: do cities act like termite colonies? Do cities get slower the larger they get in terms of per unit person metabolism? And so we'll have this in terms of this per mass rate. And so as I argued, lots of rates. When you have 3/4 scaling, rates scale as mass to the -1/4. So the faster the city or the organism, the slower the rate should be. And there are lots of ways of measuring this that I'll get to. But one easy way to do this, which is amongst my fun, most interesting amusing data sets that I came across, was if you look at walking speed. So somebody went out and documented walking speed in different sizes of city around the world. And this is no surprise to anyone who goes into London for the day to see these data, or to Lagos or to Bombay or anywhere, that the larger the city, the faster, the more of a hurry people are in, and the faster they walk in those cities. So here's something surprising. If we take walking speed as a metric of metabolic activity, cities they're not slowing down the larger they get, they're getting more active the larger they get. So cities are different from termite colonies. And this work by Louis Betancourt has looked at lots of metrics for cities in this light. And you can look at them, and some of these activities, and you can associate these things like number of patents, number of inventors, number of wages, super creative employment, whatever that is, GDP. You could say things associated with wealth creation. And the scaling factor for those isn't 0.75, it's over 1. So they're faster. As with walking speed, things are faster the larger the city. A number of other things have a scaling factor around 1, and these tend to be things that are independent of city size. So the total amount of housing, the total consumption doesn't seem to change. The water consumption doesn't change. And other things show this 3/4 scaling rule, and they tend to be things to do with infrastructure, number of petrol stations, or the length of cables, or road surface, where there's efficiencies and economies of scale in these metrics. But overall, in terms of these activities, cities get faster with increased size. So when we look at this image again of the Earth at night and see these cities blazing across the world and towns at night, one insight that emerges from this work is that cities are not like social insect colonies. Instead, they're more like stars. The larger they get, the more fiercely they burn. So they're huge reactors of social metabolic energy, where there's innovation, where there's interchange of activities and ideas, and as they're more interconnected, the more this activity occurs. And one of the challenges with this is that exponents greater than 1 have their problems. And so if you work out the mathematics of these, if the exponent is, let's say, 0.75 or less than 1, the population of a city or a termite colony tends to approach some natural limit. So there's limits to the efficiencies of size, and there's a limit to the maximum size of a colony where it's no longer worth getting any bigger because inefficiencies build in. So you tend to have an asymptote, a flattening off. If the exponent is exactly 1, you get an exponential curve. But if the exponent is greater than 1, as we see in cities, we actually see this super exponential growth, which, if it could be unconstrained, all its conditions remain the same, would actually reach a singularity of infinite growth. And that is not what happens. And the reason why it doesn't happen is that the city, or any super exponential growth, reaches resource constraints, that there are boundaries to that growth that limit it. So why, and that could lead to a period of collapse of those cities. So why doesn't that happen in the case of most cities? In some cases it does happen. And the reason, so under any one particular technology mode or governance mode, a city is approaching a singularity of exponential growth. It hits resource constraints that cause a crisis, that requires innovation, that could be in technology or in governance, and that puts it on a different curve that also tends to approach at a singularity and then requires a further innovation to break it off that curve. And so you have, instead of having exponential growth or collapse, you have this constant cycle of crisis and innovation that summarizes how cities would grow under this model. And I would argue that as cities are increasingly the way society as a whole works, this is actually represents how humanity has changed its social metabolism throughout history, and particularly its social metabolism varies in contemporary times. And in this paper by Betancourt, they look at rates of population growth in New York and suggest they see evidence of these periods of rapid growth and decline and rates of growth over time that match their model in terms of these patterns. And so this, I think, hinges on one of the key insights and arguments in the economics of our times, which is, to what extent are we in a Malthusian world where there are fundamental constraints? And Malthus came up with this idea in the 18th century. And actually, in some ways, perhaps it did describe this pre-industrial world quite well, that there are fundamental constraints, that more wealth just creates more demand rather than ultimately increased personal welfare. And this Malthusian world, a counter viewpoint comes from the arguments of Kester Boesdrop and others, that constantly innovation breaks these constraints. So whenever we're hitting a Malthusian constraint, there's a technological or a governance innovation that breaks us through to the next mode and other constraints. So rather than having a Malthusian catastrophe, we tend to have growth over time. And clearly, over the last few centuries, we've been in more of a Boesdropian world than a Malthusian world. Perhaps earlier than that, we were in more of a Malthusian world. And one of the challenges is to note what are the limits to this, or whether we can continually innovate ourselves out of crises, and how we can foster that innovation, not only technological, but also governance innovation that can push us through the challenges that we face in the 21st century. So just to conclude, so tapping some of the insights that I think that come from this metabolic viewpoint are that tapping into deep time solar energy has enabled the human metabolism to increase to a scale comparable with a natural biosphere metabolism. And a key feature is any transition that takes into account the aspirations of much of humanity. And we have to realize that much of humanity is just aspiring to reach conditions even vaguely close to the comforts and assumptions that we have in our lives. But we need to find a solution to this high metabolic energy demand. And part of it is certainly finding sources of energy supply that are not as destructive and as coal and fossil fuel energies. And that's a key part of finding an innovative solution to the challenges we find. But other parts may be governance and the way we govern our global commons and make common decisions that cross over boundaries, something that we're finding extremely challenging in our phase of history. And perhaps the fundamental environmental challenge of our time, and I would argue the defining characteristic of the Anthropocene, is that our metabolism is beginning to surpass the natural planetary metabolism. And this is leading to resource depletion, over-harvesting, habitat loss, and all the other various environmental challenges we face of our time. And so our challenge, perhaps also, as I've showed, we're in this period of metabolic growth that it seems very hard to see that continuing indefinitely into the future. It's almost that singularity that appears in those models of Betancourt. And we are hitting, not only at a level of a single society, but as a global society, we're hitting the constraints that are challenging us to push away from that pathway to a singularity into new pathways. And this will require innovation both in technology and in governance. So, as I said, many of these arguments are made in the book chapter if you want to follow them through or see the references to many of the points. I'll also make this presentation available on my website by tomorrow morning if you want to see the slides and look at them more slowly, and the web link is there. So, thank you.
Thank you very much, Yadvinder, and I'd like to apologise for our issues with the lights. Right, we've got plenty of time for questions, and I think we'll, try and work our way through everyone. So does anybody have anything to kick us off with? Towards the middle... Oh, no, hang on, I'll take it.
No, hold it, because I have to read out my question. Hi, thank you very much. I want to ask, so suppose that we find a source of energy like the sun, so it's supposed to be like an unlimited source of energy. But then if wealth leads to more demand and leads to more growth, wouldn't that still find us trapped in an innovation crisis cycle? And so my question ultimately is, would outsourcing our energy to outer space ultimately not change the fact that there are physical constraints on the Earth? So if we find innovation to go past the singularity of energy found on Earth, well, we would have still more demand for Earth's resources. So wouldn't we still be in a Malthusian model?
Yes, I think that's a very good point. That many of the aspects, the climate change crisis is caused by one aspect of our metabolism, which is that our primary energy source emits a waste product that's changing the atmospheric conditions. If we can solve that technological problem, essentially, I think, which it is fundamentally, at some level, we still face the fact that the more energy we have, the more we transform the biosphere around us. So I think all of these solutions aren't a fundamental solution. I think, to be honest, I don't know whether there is a fundamental solution out of the mode of human history, which is that all of human history, when we're not in some sort of growth crisis innovation model, we're trapped in a fairly static mode, which also has its challenges. We're vulnerable to shocks. I think this is how much of the medieval world was. It wasn't a more equilibrium-based, happy place of sustainability. It was a place where external shocks cascaded through the system, whether there were epidemics or invasions, and caused crisis, calamity as well. So whether growth or stasis seems to have challenges about it. But certainly, even if we solve the energy problem, I think it's only one aspect of the other impacts we have. And I think the solutions will be piece by piece in that same sense. The energy problem would be solved if we solve the fundamental problem, which is the waste products of our energy. Our biosphere problem may have to be solved in a different approach to governing the biosphere that enables the natural processes to be sustained, the ecosystem services of the biosphere to be sustained. And so some of the innovations in other places may not be so technological. They may actually just be in our governance modes and our ways of managing ocean resources or land resources.
Next. So if we take the one at the back and the one in the middle we'll take two together.
Well, I don't understand why you've got a picture of Ghanaians studying in school in one of your slides.
Okay.
Why have you got a picture of them?
Okay. Well, one of the arguments I make. This is my daughter asking the question, as always, and is that from all the challenges that we get from the biosphere. From all the changes that we're making, there are also lots of benefits and good things coming to lots of humanity. And one example is that the increasing electricity supply, energy supply in Africa is beginning to pull many people out of poverty. In the case of Ghana, in that example, the education rates, the school enrollment rates, the healthcare rates have increased rapidly. And they're all linked to the fact that Ghana has a lot more energy available, has moved away from a rural poverty situation to an increasingly semi-urban, semi-industrial situation. So many of the good things also come from this increased energy and the increased education opportunities that are available to much of the world as one example of that.
Hello, thank you for the very interesting presentation. In one of your slides, you had this global social metabolism has reached about 17%, and you posed the question whether this is a big or a small number. We have to consider how much we want to leave for the other other biodiversity of the planet. Mm-hmm. And I was wondering, to what extent do you think that our social metabolism can be shared? As in, is it really the cut boundary between giving or leaving some? Or is it more about kind of a blurred line between that? And to what extent do you think our practices of how we metabolize can influence how much we share?
Mm-hmm. I think that's a very good point, and it isn't either or. Isn't this is actually one of the major questions in conservation? Is sharing versus sparing in terms of land. To what extent can you mix in biodiversity conservation into land use? As one example of this, and do you try and have agricultural systems that don't completely obliterate biodiversity but allow some ecological function to be maintained, or is it more efficient to have this sparing idea where you intensively farm areas that are suitable for agriculture but leave other parts of the biosphere in a relatively wild and intact state? So that is one sort of encapsulation of that argument. And I think there's certainly possibilities are for both. I don't think it's an either-or situation. There's certainly areas of in our farming practices that can be made more sustainable, less damaging in terms of function, as one example. But also, there's a room for wild lands, and I think it would personally be a tragedy if every part of the biosphere became a farm of some sort, from my perspective.
Okay, so we'll come down the front and then back to the middle.
Thank you. Yes, fascinating. Thank you very much. I'm really worried about the conclusions, though. I mean, I'm not keen on any of the technological innovations that are going on, such as nuclear power or even all this cyber stuff. I think it's very dangerous. And the governance. I mean, governance is all wrong. I mean, they stress this sort of technology, and as soon as the oil price goes down, instead of thinking, oh, well, let's kind of, stabilize a little bit. Oh no, we can have some more growth, more growth, more pushing at the other barriers all the time. And I really think there's something very wrong with the attitude. I mean, none of these conferences about trying to limit climate change or anything ever seem to come to anything because people don't really want to. They want to have more and more and more and more. And you say, oh, well, if we have 120% if everybody's living like the Americans, everybody does want to live like the Americans.
Could I ask you to get to your question?
Sorry.
Thank you.
How can we get the governors to start thinking, oh, perhaps we should try and persuade people that it would be better to live on a lower level of consumption and population growth? As a matter of fact, the rich have lots of children. How can we persuade the governors, the media and everybody else that this is the way to go, not to get more and more and more all the time?
Yes, so I think part of that is about governance, and part of that is about behaviour as well. And I think the challenge there, as I mentioned, is that this norm that we have of constant rapid growth is only a few generations deep in human history, but it's become the default assumption of how our global economy works. And it's not obvious if we go off that curve, what happens as well. So even a recession tends to cause various cascades and instabilities in the system as well. But certainly I think a key thing is to recognize that the mindset has to change, that we need to, and it is a challenge, it's a double bind, we need to meet the aspirations of much of the world to live better than they do now. But it can't entirely be on the same pathway of rapid, well, it is at the moment, but if it carries on, we're in trouble, which is of rapid fossil fuel-based growth that just ends up dumping more into the atmosphere than the atmosphere can bear and feeds back to cause detrimental problems there.
We need some kind of redistribution from us to them in order for them to have more. Not them to have more and us to have more and everybody to have more, but we could have a bit less so that they could have more, and then there would be some state.
Yeah, I think how we can make that happen is a challenge.
Exactly,
but that's
you people, I want you to make it happen. You've got all this influence, please make it happen.
okay, we'll try our best.
Any more questions? Okay, so we'll take one from here and then the same side, a couple of rows further behind.
You were pointing out that much of our energy use is coming from the consumption of fossil fuels.
Mm-hmm.
So I wanted to ask, had you made a considered estimate of how many years it took the planet to store the fossil fuel that we burn in a year? I think a back of the envelope calculation, it's about 10 million years worth of fossil fuel burnt every year.
Yes. I can believe that number, that the rate of accumulation of carbon in the lithosphere is very, very slow. And
Caroline, just here. Oh, sorry, I thought there was one other here. Yes, please go over there. Sorry, hands went down.
Hi, Yadvinder. You're relieved to know I'm going to ask you a data question and not how to solve the planet's problems. I don't know if it's worth flicking back. The Betancourt idea that we reset the singularity point by repeated innovation. One of the interesting things you'll notice there is that the need for innovation gets faster and faster as time goes on. Mm-hmm. Now, there's a sort of idea here that it's either a problem or we innovate and it's all fine. I'm just wondering, doesn't innovation require energy? And therefore, if we accept that energy use is any reasonable proxy of a problem, then does innovation in the end, do we know, data-wise, whether innovation actually ends up using a lot of energy or whether it ends up saving energy?
Yes. I don't know on data side what the answer is. I would assume that innovation doesn't always come with an energy cost. You could think, for example, a city developing an efficient public transport system that would actually reduce the energetic metabolism of that city. And that's a mixture of a technological and a governance innovation. It's saying that let's govern the transport of that system collectively. And I think in the case of New York, they're part of the reason why you see those curves going off as the transport system changes in New York. So I think for two reasons innovation doesn't need to consume more energy. One is that it can be innovation in governance systems and how we rearrange the transport system of a city, for example. And two, many of our innovations now are highly technological and they're not necessarily energy demanding. They actually can have, for example, I have one example going from tungsten bulbs to low power light bulbs. It has the opposite effect. The innovation actually pulls us down on the metabolic curve.
The gist of your talk to me seemed to be that there may be trouble ahead, and even if it wasn't, I sometimes find it more empowering to assume the worst and ask what then can we do. And the other thing I noticed was if we sort of project what you showed and look forward, it didn't seem to take account of external shocks, large volcanic eruptions or black swan events, wars and so on. Do you think we're going to have a smooth ride in the next 50 years and given the governance as you see it, without having some big optimism bias? And should we prepare for some large shock as we come up against some of these limits?
Well, that's a big question. I think certainly there are huge challenges. There certainly is no business as usual throughout this century. So when we look at these projections for 2100 in terms of emissions and population and things, I think a lot of that is pie in the sky, because the modes of society, the challenges society faces are huge before then. But also the technological changes are huge between now and the end of the century. Just as if you go back a century, if we were standing here a century ago, could we have predicted the challenges and shocks the system faced over the 20th century? No, pretty effectively. And so I think there will certainly be huge challenges. And in some ways, perhaps we've gone through a very quiescent phase of human history in the last 50, 60 years, where we've just had metabolic expansion with no major shocks to the global system. And as we hit constraints, it's quite likely we will hit very shocks. And climate change may be one aspect of those, but certainly not the only one.
Right, we've got time for one or two more questions. Does anybody have one? So we've got one here.
If all of the fertile land in the world was used for intensive farming, do you have any figure for what size of global population that could support?
Not off the top of my head. The large areas of readily accessible fertile land are in the tropics. So fertile in the sense that with heavy industrial inputs, they can be highly productive, such as the agricultural industries of Brazil and Asia. I think you could. This is not my area of expertise, so I'm not going to sort of give a number to that. I think you could probably support more people, but at cost in terms of Earth system functioning, in terms of biodiversity and habitat. So even that scenario, I'm very hesitant to move to a world where we've converted every bit of land to human consumption. And as a tropical forest scientist, I see much of Asia being covered in palm oil plantations to provide for various things, but particularly for foodstuffs is a big source. And so you could certainly envision a world where that could come from Africa and the Amazon as well, as an example of how much more production you could get out if you chose to purely see things through a production lens. But I don't have an exact number for those arguments.
Any more questions? We've probably got time for one more. Back to you.
Do you have an estimate of how much energy we would actually need if we were to live just a satisfying life, but equally long as the ones we do?
I'm sure that we could define what a satisfying life is, but I'm sure you could even work out the social metabolism of different people living different satisfying lives in the UK. And you'd see that people's metabolisms are very different in size, depending on where the energy comes from. How much meat they consume is a big part of their social metabolism as well. I can imagine, if we chose to in a modern industrial society, our extended metabolism could be not that different from a pre-agricultural one. Of around 2,000 watts, 3,000 watts. But part of that extra is, a lot of that metabolism isn't directly in our immediate sort of luxury consumption. It's also in the infrastructure that provides us with school and healthcare and policing and the public infrastructure. Our social metabolism is all of that as well. So there's probably a minimum level there if we want to keep the benefits of all those things that we have, which is probably substantially smaller than the 8,000 watts we're at, but I'd say I'd venture around 3,000 to 4,000 perhaps. But it's probably quite a number we could work out if we choose to.
Thank you very much, Yadvinder. I think that's been a brilliant start to the term's seminar series. Please do come along. We've got seminars every Thursday, like I say, all about these issues, about how we manage climate change, the risks, what we can do to mitigate, all leading up to Paris 2015 and the COP negotiations. So for today, please join me all in thanking Yadvinder for a great seminar.